Welcome back. This is part 2 of the motion review video. Today we're going to be looking at free fall, which is it's very interesting, and this has to do with constant acceleration. Little g, a lot of people think little g means gravity because it happens to start with a g. That's wrong. Little g is not little g is not gravity. Little g is not the pull of the earth. That's called weight. Little g is the acceleration due to gravity. Notice the units for little g are acceleration units. It's the acceleration due to gravity, and all objects in a vacuum, whether you're big or small, are all accelerated the same. They're not pulled the same, they're accelerated the same in a vacuum. That's what little g is. Now, if you go away from the Earth will take away about 10 meters per second of your speed every second. If you come toward the Earth, I'll add about 10 meters per second to your speed every second. It's still constant. It's still constant acceleration. Your velocity will be changed by about 10 meters per second every second. And that's what little g means. Little g is equal to about 10 meters per second squared, sometimes written as 10 meters per second dot second, or old school 10 meters per second per second. This is motion 2, the video, the sequel. Now let's go to here. The chart I'm going to ask you to do is, let me find it for you. The chart is on free fall, and what you're going to be doing is we're going to be drawing the free fall thing. Free fall is a special case of constant acceleration. And you know that it has to do with free fall because both equations have little g in them. Free fall, how fast, velocity or your speed equals little g times time, v equals gt. And how far did you go under constant acceleration? Distance equals 1/2 gt squared. Okay, so those are the two equations we're going to be using for here. Excuse me. All right, now I went ahead and wrote these out, but you can take your time on this. But the first thing you want to do when you want to write this, let's say I was going to redraw this chart. What if I wanted to redraw this chart? How would I redraw this chart? Let's find one here. Well, first of all, I would draw the object at rest. Here it is. And then I would draw it a certain distance here. Now that little distance there, I'm just going to call that a chunk. It's a chunk of distance. Now where do you draw the next dot? If this is one chunk of distance, you draw 1, 2, 3. This would be 3 chunks of distance. And this would be 5 chunks of distance. And this would be 7. This is Galileo's odd integer pattern. If something undergoing constant acceleration, it'll travel 1 chunk of distance in the first time period, 3 times that far, 5 times that far, and 7 times that far during the successive seconds. So that's how you start your drawing. Here's my time, 1 second, 2 seconds, 3 seconds, 4 seconds. Now, how fast is the object going to be going? Well, you said free fall, how fast? What are we going to be using? We're going to be using V equals GT. Plug in 1 second there, 1 times 10, and you get this. At the end of 1 second, you'll be going about 10 meters per second, 20 meters per second, 30 meters per second, 40 meters per second. That makes sense. Look, velocity and time are directly proportional. See that? As the time gets 3 times further, the speed gets 3 times higher. Okay, the next part is, let's take a look about average speed. What is the average speed during the first second? And this is kind of complicated, but what happens is it's going 0 there. It's not going 10 meters per second until the end of the first second. So it's really going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Eventually it gets to be 10 meters per second. It spent half of its time below 5 and half its time above 5. And add these up, the average is 5. What is the average speed, total distance divided by total time, during this first second? It only averaged 5 meters per second. Okay, what would be the average between here? 10, 20, what's the average? 15 meters per second. What's the average here? 25 meters per second. What's the average here? 30, 40, 35. During this time period, he averaged 5 meters per second. Now think about that. If you average 5 meters per second and you travel for 1 second, how far will you go? 5 meters. So at the end of 1 second, he's traveled a total distance, at the distance of 5 meters. How far will you travel during the second? Okay, during the second, the average is 15 meters per second. I travel for 1 second, so I should travel about 15 meters during this second. How about during this time? I should travel about 25 meters per second, and during this one, meters, 35 meters during this second. Now this is interesting. This is called there's 1 chunk, 3 chunks. See, 5 is a chunk. 3 chunks, 5 chunks, 7 chunks. That's Galileo's odd integer pattern. But what if you want to know the total distance from the beginning? That's when you use the d equals 1/2 gt squared, total distance. Total distance is, all right, let's put in here 1 second. 1 squared is 1. 1/2 g is 5. 5 times 1 is 5. The total distance would have been 5 meters. Plug in 2 seconds here. 2 squared, 4. 4 times 1/2 g gives you 20, 45, 80. This is the total distance. What's neat is 5 is total. What's 5 plus 15? 20. What's 5 plus 15 plus 25? 45. What's 5 plus 15 plus 25 plus 35? 80. Ooh, it all works. This is how you should be able to redraw this chart. And if you can redraw it on a blank piece of paper, I think you'll understand free fall. Okay, in another chapter, we'll learn that ramps, for example, can give constant acceleration, but it's not going to be anywhere close to 10 meters per second squared. It may only be like maybe 2 meters per second squared, like that. Well, this just has to do with free fall. I hope it helped. Again, you can watch these videos more than once. And again, tomorrow, Friday, will be where you have your test. So you can watch the videos as much as you want before that. All right, thank you very much.